Good morning. Today we'll be talking about our project device, which is a speech-to-Braille translator device for deaf-blind people. Deaf-Blind Australia defines individuals with deaf-blind disability as those suffering from both hearing and vision loss or impairment. In 2017, 13,000 of Australians under the age of 60 live with a deaf-blind disability. While a variety of products exist for individuals with visual disabilities or individuals with hearing impairment, few technologies cater specifically to individuals suffering from deaf-blindness. Motivated by this information, our group focused on developing a product to perform real-time speech-to-Braille conversion to make it more convenient for deaf-blind individuals to communicate and complete everyday tasks. An overview of our system is shown on the screen. Software on the smartphone will allow a user to connect to our device wirelessly and transmit a message. On the device, the microprocessor will translate each character of the text into a 6-bit binary number. The 6 bits will correspond to the 6 dots in Braille. Our project was constructed on an Arduino DUE board and a Bluetooth shield. The Braille actuators are made from 5-volt push-pull solenoids with restoring springs attached. Since the 3.3-volt output from the Arduino digital pins is not enough to drive the solenoid, a TIP102 BJT is added to amplify the voltage. A diode is connected in parallel with the solenoid to prevent damage to the circuit while it is discharging. A button was connected so the device user can interrupt the message being transmitted. When the button interrupt is triggered, it will clear the current message being displayed and clear the Bluetooth buffer on the DUE. A 3D case was designed on AutoCAD to keep the solenoids in place and generate a coherent Braille pattern. The circuitry and Braille actuating circuits are shown on the screen.
The software on the phone was developed using Android Studio IDE, which is based on the Java language. When the program first started up, the program retrieved the MAC address of currently paired device and appended it to the paired device list. After selecting the device they wish to connect to, the app will show option to pick either a text input or a speech input. If the speech input is chosen, Google Voice Assistant will be activated and will keep recording speech until no speech input is detected for 3 seconds. This voice message will be converted by Google Voice Assistant into text type and displayed on the screen for the user to verify. For example, if a character X is detected, it will be transmitted as a character type to the Braille device. On the Braille device, the AppMan chip will convert the character into its ASCII form 100, which is mapped by a special function to 6-bit binary number 101101 and finally transmitted to the solenoid, which will display the corresponding pattern.
The layout and functionality of the phone app is shown on the screen. And now we will demonstrate the project. During testing, the subsystems were tested separately, and the Braille actuators were initially tested with LEDs to verify their correctness. We used available apps in the App Store to test the Bluetooth shield along with the actuator. In app development, the first step was to establish connection successfully with the device. We then tested the ability to send string messages over Bluetooth, and finally adding the Google Voice Assistant function to convert speech input and send it to the device.
The main problem that we faced were in the software development stage. One of those problems was pairing. Our initial approach involved searching for all Bluetooth devices nearby, which was unreliable and slow. We decided to use a new method to pair with devices that are already connected to our smartphone through Bluetooth previously. This made it much easier to find and successfully pair with the correct device. We also did a bit of debugging, especially with using Google Voice Assistant and transmission of message between the phone and the Braille device.
There were a few main limitations to our current design, mainly that the solenoids are bulky, inefficient, and can heat up over time. An improvement would be to use piezoelectric strips, which are lighter, easier to operate, but require higher voltages to drive. Another improvement to our design will be using Wi-Fi shields for communication over longer distances. Thank you for paying attention.